A bag is generally dropped on a conveyor belt moving at a speed of 2 meters per second. The coefficient of friction between conveyor belt and is zero point 0.4. Initially, the bag slips on the belt before it stops due to friction. The distance traveled by the bag on the belt during slipping motion is. Now, see, this is one such question which will evaluate almost every concept that you have learned in this chapter so far. I mean, I would say, it covers laws of motion. It covers laws of motion, and it covers brilliant aspects of friction as well. Also, it is very much linked to relative motion that you study in your second chapter. Okay, so this is a very good question, and these kind of questions also give you an insight on the comparison between inertial frame and non-inertial frames. We'll do this question in two ways. First, we'll do it the inertial way. Second, we'll do it so solve the questions in a non-inertial frame of reference. But before going to that, let us dissect the question. So what's given to us? A bag is gently dropped. See, each and every word here that I have written here is of much importance because it can alter the pace of the solution. Let's take them one by one. So we have gently dropped. So what would that mean? How would a question vary if the question would have said suddenly dropped? So to explain that, let me take you through one small explanation here. Okay, what do we call this as? So if the bag is gently dropped, okay, if this bag is gently dropped, what's going to happen here is this bag is slower, it's lowered slowly, and it is kept with the on the belt, and slowly it will start moving along with the belt. Okay, I repeat, if the bag is lowered slowly, it will come into rest, then it will slowly move along the conveyor belt and eventually attain the same velocity as that of the belt. Okay, now what will happen if you drop it suddenly? If you drop it suddenly, this bag will come down like this. It will bounce, settle down, and then move with the velocity. Okay, so let's take this one more time. If you slowly keep a bag on the moving conveyor belt, its initial velocity would be 0, and it will pick up the pace. It will slowly accelerate, and then it will keep on going along with the same velocity as that of the belt. Okay, however, if you drop it suddenly, what will happen? It will fall on the belt, it will bounce maybe a couple of times, and then it will acquire the velocity of the belt. Okay, so this condition would make the problem really complex to solve. Okay, so that's why the question specifically says gently dropped. Okay, so that's that. Now let us try to understand the next set of statements. Coefficient of friction, kinetic or static. Initial, well, it should be very clear to you that the friction here is not static, rather it is kinetic. Why? Because there is a relative motion between. Why? Because there is a relative motion between the bag and the conveyor, right? So therefore, it should be the kinetic friction. Now, initially the bag slips. What does it mean? What does it mean when we say the bag slips? If the bag slips, it means that the relative velocity of A with respect to B is not equal to 0. So slipping condition means that there is some amount of relative motion, and it is not that relative velocity is equal to 0. It is the case that relative velocity is not equal to 0, and therefore the bag slips. Okay, now it stops due to friction. See, something which is very interesting here is this is one peculiar example where friction actually results in acceleration of the body. Okay, usually what is the case? Yes, we know that friction is a retarding force. But here in this example, we'll come to know that friction is actually resulting in acceleration of the body rather than retarding. But having said that, we also need to say that although it is resulting in acceleration, it will definitely oppose the relative motion. Okay. Now, what a slipping motion implies? Slipping motion implies that there is some amount of relative motion and not absolute motion. What is that point? We think will become more clear to you once we solve the entire question. So, part one, I would like to solve this question using the inertial frame. So now you may have a doubt what is inertial, what is non-inertial. See, every concept will become clear to you once you pay your maximum attention and once you solve this question on your own without looking at this solution. Okay? Right. See, you can revisit the solution, but don't try to copy down things. Okay? Listen to the solution once, then try to figure it on your own. And if you come across any doubt, come back again. Okay, let me now take you to the difference between accelerating and non-accelerating frames. Okay. So what is the frame of reference? Frame of reference in its very simple term is the location, okay, where the observer is present. Or in other words, simple words, location of the observer. Now the location of this observer could be two. It can be a stationary location, or it can be a mobile location. Okay. If the observer is standing in a stationary location, then that frame is said to be an inertial frame. Okay. If the observer is present in a mobile location, then that corresponding frame is said to be a non-inertial frame. Inertial frames are otherwise called as non-accelerating frames, and non-inertial frames are otherwise called as accelerating frame. Okay. Now, one simple example to understand this would be a person. Okay, say for example, instead of conveyor belt, try to assume that this is a bus, and you have one person, or maybe somebody is sitting in the bus, and you are observing the person. Okay. So what's happening here? The person is moving like this. The person is moving like this. And we need to understand that in this specific case, it is not just the person, but the person is moving. Say, let us call this as VB. And at the very same time, what else is also moving? The conveyor belt is also moving. So we have velocity of conveyor belt as well. So we can see as a person standing outside the, now where is he standing? That's also important. He is standing somewhere over here on the road, which is the ground, and the ground is stationary, right? So the person is observing the man or the object which is inside the bus, which is moving with some velocity VB, and the bus is also moving with some velocity VC. In this case specifically, it is moving with a, so this is the conveyor belt. The conveyor belt is moving like this, and we have velocity of block like this. Okay, so we have one object. We have one object which is moving like this. Okay, which is like this, and we have a moving conveyor belt. Now, what is accelerating frame? Accelerating frames means the observer who was standing earlier in the ground is now standing within the moving conveyor belt, and the object moves, and at the very same time this person is also moving when the object is in motion. Okay, so here the velocity that we measure is velocity of the bag, velocity of this bag with respect to the conveyor. Okay, So here the person is observing two different velocities, one that of the bag Vb and the other that of the conveyor belt Vc. Whereas here the person is observing the bag, but where is he standing? He is standing on the conveyor. Therefore, this velocity becomes velocity of the bag with respect to the conveyor. Okay. To be more precise, where is this man standing? He is standing on the ground. What is he observing? The block or the bag. So what is the velocity? It is velocity of the bag with respect to the ground. So this is actually VBG. Where is the man standing? He's standing on the ground. What is he observing? He's observing the conveyor belt. So what is this velocity? It is velocity of the conveyor belt, to be more precise, with respect to the ground, right? With respect to the ground. All right. So I hope these things are clear. Now we will use only the first method in this session to solve this question. Okay. So solution using which frame? Inertial frame. Okay. Okay, so sorry for the delay. So now what we'll do is we'll try to understand the non-accelerating the frame or the inertial frame, right? Or the inertial frame. So what's happening here? A person is standing on the ground, and what is he observing? He's observing two objects, one which is the bag and the other which is the conveyor belt. Okay. Now, what does he measure here? Velocity of bag and velocity of conveyor. To be more precise, velocity of bag with respect to where he is standing ground, velocity of conveyor with respect to where he is standing ground. I hope this much is clear. Okay. Okay. Now let us see some points here. So this bag is moving in this direction, right? It is dropped. It slowly comes in contact with the bag. There is some inertia here, and then it will slowly move like this. Okay. Now see, this represents velocity of. Okay, sorry. This represents direction of motion of the bag. Okay, direction of motion of the bag. And what does this represent? This arrow here represents direction of motion of conveyor. So now things are going to be really conceptual here. Make sure that you give your maximum concentration here. This conveyor is moving towards the right. Am I correct? Yes. I hope there's no doubt in that. The bag is also moving towards the right. Okay. Now, if the conveyor is moving towards the right, tell me what would be the friction which is acting on the conveyor due to the bag? Friction will oppose the relative motion, right? So, this force here, this vector here would be the vector which shows friction acting on the conveyor due to the bag. Now look at the concept here. This friction is not acting on the bag. Instead, this friction is acting on the conveyor belt, which is acting due to the presence of bag. Okay. So what is the concept now? If we know by Newton's third law of motion, if bag is exerting a friction on conveyor, definitely conveyor should exert some friction on the bag as well, which has to be equal and opposite. So which can write equal and opposite. So this is friction on conveyor due to belt, and there should be equal and opposite, which we can write it as friction acting on block due to conveyor. So if we were to represent that, it would look like this. So we have now friction acting on the bag. So this is friction acting on the bag due to the conveyor. Okay, I hope that much point is clear. Now, please revisit this. This is really important. This concept is really important. You have to understand you should have clarity in this. Now, if I draw the free body of the bag, what are the various forces acting on the bag? The first force definitely would be the normal reaction on the bag due to the conveyor. The second force would be, we know, would be the weight of the conveyor which is acting downwards, and the net direction, let me just write it down here. So the net direction of motion is towards the right, and the only force acting here is friction, but we know friction is acting in the same direction. So this is friction acting on the block due to the conveyor, right? Now, when we consider free body diagram of the bag, we don't consider forces acting on the conveyor. Okay. Now, sigma Fy is equal to 0 and sigma Fx equal to 0. Why? This is because the object is in equilibrium. Sorry, my bad. It's not 0 here. It should be ma. But sigma Fy is equal to 0. Why? Because there is no net motion in the which direction? In the y direction. So what does sigma Fy is equal to 0 implies? As we say, it implies F up is equal to F down, which means forces acting in the up direction should be equal to forces acting downwards. The only force acting here upwards is NBC. So we can write normal reaction is equal to only force acting downwards is mg. So this is N is equal to mg, right? Okay. Now, what is sigma Fx is equal to ma implies? A implies acceleration in the x direction. We'll take it as ax. But there is no ay. So if you keep the logic here, is actually a net is equal to root of ax square plus ay square. Since there is no motion in the y direction, what is 0? Ay is equal to 0, and therefore a net will be equal to root of ax squared will be equal to ax. Okay, so I can essentially replace this ax as a. Now let's see the forces. The direction of friction, this is the direction of motion. So since friction is acting along the direction of motion, we will take that as positive, and therefore friction here is acting positive, which means friction is now causing the acceleration instead of retardation, right? Okay, so we have plus mu k into n is equal to mg. Now what is n? N from this equation is equal to mg. So mu k into mg is equal to m into ax. M by m is 1. So we have mu k into g is equal to a. So a is equal to mu kg is what we have. Now let us see this condition here. So here, if we analyze the motion of the bag, it started from rest. This is where the first animation, not the animation, the illustration should come into your picture. Initially, when the bag was kept on the conveyor, its velocity is 0. And slowly it will attain the same velocity as that of the conveyor, which is moving at 2 meters per second. Therefore, the velocity of the bag at the final stage will be 2 meters per second. Right? Why? Very good. See, these kind of questions make you think, because the distance, belt, it stops due to friction, right? Initially, the bag slips on the belt before it stops due to friction. So it does stops due to friction. Now, when it stops due to friction, when it is moving within a conveyor belt, what can we say about the velocity? Sorry for the lag here. So when it is moving, when it is stopping on the belt, it means that the bag has acquired the same velocity as that of the conveyor belt, which is 2 meters per second. So it essentially means that the relative motion is now stopped. It has stopped due to friction, right? It has stopped due to friction. Now, when it has stopped due to friction, friction opposes the relative motion. Or in other words, what is the duty of friction? Duty of friction is to make the relative velocity equal to 0, and therefore velocity of block with respect to conveyor in the final stage will be equal to 0. And therefore we can say that VBC is equal to 0. What is VBC? VB minus VC equal to 0. What does that imply? Velocity of belt is equal to velocity of conveyor, and therefore velocity of belt bag is 2 meter per second. Okay. So initial velocity is 0, final velocity is 2, and we have Ax is equal to G into mu k. Now what? Now, we know by Newton's equations of motion that final velocity square minus initial velocity square is 2as, v is 2, initial velocity is 0, 2 minus 0 square is equal to 2 into acceleration is mu k into g, and s is into s. Now, why mu k? Of course, because there is some relative motion here. The friction has to be kinetic in nature. 2 square minus 2 square is 4. 4 minus 0 is 4. Mu k is given to us as 0.4. G is 10. So this becomes 2 into 0.4, which is... Okay, how did I do this? 0.4 into 10 is 4. 4 by 4 is 1. 1 by 2 is... My bad, it is not 0.2. It should be 0.5. Therefore, the relative distance moved here is 0.5. Okay. Now what we'll see is, so far we discussed the non-accelerating frame, and this time we'll see the case where the observer is also standing on the conveyor belt, but I think I'll do it as a separate one.